students, welcome to this lecture. In today's lecture we will discuss a geometrical method, geometrical ideas based method to solve a nonlinear first order PDE, which is known as Cauchy method of characteristics. So, let us start with the Cauchy method of characteristics to solve a first order nonlinear PDE. So, as I mentioned earlier, here we are going to discuss a method based on the geometrical ideas and is due to Cauchy, and to solve the nonlinear partial differential equation, the general first order PDE in two variable x y has the following form: f x y z, and the derivative partial derivative of z with respect to the independent variable x y, that is deriv z by deriv x and deriv z by deriv y. And here we assume that f has continuous second order partial derivatives with respect to its arguments, that is x y, and also we assume that f z x square plus f z y whole square is not equal to 0. The idea behind this is that this equation number 1 is not independent of z x and z y. So, in fact we can always solve this f x y z deriv z by deriv x and deriv z by deriv y either in terms of z x if f z x is non-zero, and in terms of f z y if f z y is non-zero. And let us denote, for simplicity, let us denote that p equal to deriv z by deriv x and q equal to deriv z by deriv y. So, in terms of p and q, we can rewrite our equation number 1 as follows, that is f of x y z p q equal to 0, and our aim is to solve this first order nonlinear PDE using the geometrical geometrical ideas. So, to do this, first let us do some basic things. So, first you just recall that the plane passing through a point p x naught y naught z naught with its normal parallel to the direction n, which is defined by the direction ratios p naught q naught minus 1, is uniquely specified by the set of numbers t of x naught y naught z naught p naught comma q naught. In fact, if you look at any plane and take any point which you call as p, and let us say that this is x naught y naught and z naught, and if it is this point is lying in a plane, then if you know the say normal vector which is, let us say that p naught, say p naught q naught and minus 1, here p naught is your z of x given at the point p, and q naught is equal to z y given at point p. So, if you know the direction vector let us say n, then you can write down the equation of plane, and equation of plane you can write it like x minus x naught say z x plus y minus y naught z y equal to z minus z naught. In fact, you can always write it like this equation: x minus x naught f of x plus y minus y naught f y plus z minus z naught f of z equal to 0. If your equation is given as f of x y z equal to c. If your equation is given like f of x y z equal to 0, then equation of the tangent plane you can always write it like this. So, any plane you can say characterize by the point and the normal vector at that particular point, and if it is a plane, then you can characterize that plane by this 5 tuple, that is x y z and p comma q. So, conversely, any such set of 5 real numbers define a plane in 3 dimensional space, and for this reason a set of 5 numbers t x y z p q is called a plane element. So, whenever we have these kind of 5 tuple, we say that it is a plane element of this space. Now, a plane element whose component satisfied an equation f of x y z p q equal to 0 is called an integral element. So, it means that if a plane element satisfy the partial differential equation f x y z p q equal to 0, then we call this plane element as an integral element. So, these are some definitions which we want to write, and so these are called integral element at a point x naught y naught comma z naught. Now, it is already given that f p square plus f q square is not equal to 0. It means that we can always assume that either f p is non-zero or f q is non-zero at any given point. So, let us assume that f q is not 0, then we can always solve our equation f of x y z p q equal to 0 in terms of q, that is q equal to g of x y z comma p. Now, here it indicates, this equation indicate that p and q are not independent at any given point of the any given point. Now, we can calculate q when we know the value of x, y and z and p at a given point. So, keeping the point x naught, y naught and z naught fixed. So, given a point, now you vary your value of p, and when you vary your p, we can obtain a set of plane element x naught, y naught, z naught, p g of x naught, y naught, z naught, p, which depend on a single parameter p. For example, if you look at this at this particular point, that let us say it is x naught, y naught, z naught, and you then you take a p and you can get a value of q, and you vary your p, then you can have different values of say q. So, we can have different values of n here, right. So, in this way you can say that your tangent line, this can say trace a figure like this, which is having vertex at the point p, and here you can say that at every point you have this tangent vector, here you have another normal vector. So, we can say that these plane element trace a kind of curve which is we know as elementary cone. So, that we are writing it like this: as p varies, we obtain a set of plane elements, all of which pass through the point p and which therefore envelop a cone like figure and whose vertex is p, and the cone so generated is called the elementary cone or Monge's cone, right. And this is the Monge's cone defined at the point p. So, the cone is like this, this is what we call is Monge's cone, right. Now, here the term cone is used for any surface generated by a one parameter family of straight line passing through the fixed point, that is vertex. And here if you look at the p is your one parameter, here you are varying your p and you are getting a line passing through this point p, that is x naught, y naught, z naught. So, here we are getting a surface at a point p by varying your p, and we call the generated surface as a cone, and we call this cone as Monge's cone. Okay. Now, how this is related to find out a solution surface of the partial differential equation? For that, let us consider a surface S whose equation is z equal to g of x y, and if the function g x y and its partial derivative g x and g y are continuous in a certain region, say R of the x y plane, then the tangent plane at each point of this surface S determine a plane element of the type x naught, y naught, z g x, g y. So, at any point of the surface S, it determined a plane element like this. Now, this plane element we call as tangent element of the surface S at the point. So, it means that you look at the surface and look at the plane element here at any given point, and we call this plane element as tangent element. Now, once we have a tangent element, then we can say that on the geometrical ground, if this surface S is a solution of the given PD, that is the integral surface of the PD f x y z p q, if it touches at every point of the surface, it touches the elementary cone, or you can say it touches the Monge's cone. So, that is what we summarize in a theorem 3. The necessary and sufficient condition that a surface be an integral surface of a PD is that at each point its tangent element touch the elementary cone of the equation. So, it means that a given surface is an integral surface provided that at every point of the surface it touches the Monge's cone generated at that particular point P. So, now we want to find out the integral surface using this geometrical idea, and we are trying to find out this integral surface as a totality of curve lying on the surface. So, for that we just look back to the curve, and here let us say a curve C with parametric equation x equal to xt, y equal to yt and z equal to zt lies on the surface z equal to g of xy. Now, it will lie on the surface if it satisfy this equation for all t. So, it means that zt equal to g of xt comma yt for all values of t in some interval, say let us say this is I. So, for all t in this interval I, your xt yt zt satisfy this relation. Now, if p naught is a point on this curve, so you have a curve and then you, so it means that it is like this, we have a surface kind of thing and you have a curve like this which we call as C. Now, take any point here, let us say this is p naught and this is corresponding to the value of t at say t naught. So, let us say p naught then the direction ratio of the tangent line p naught p1, let us say you take one more point say p1 on this curve, and then you can always find out the direction ratio of the tangent line p naught p1 are x dash t naught, y dash t naught and z dash t naught, where this derivative represent the derivative of xt yt zt at the point t equal to t naught. So, you can find out the drs of tangents and it is given by x dash t naught, y dash t naught and z dash t naught. Now, we say that if this tangent line is perpendicular to the normal vector at this particular point, say let us say you have a normal vector say n and it is given as say p naught, q naught and minus 1. So, we say that if this direction will be perpendicular to the direction p naught, q naught and minus 1, then this then we have the following relation, that is z dash t naught equal to p naught x naught dash t naught plus q naught y naught dash t naught. So, here we have this x dash t naught comma y dash t naught comma z dash t naught dot this p naught, q naught and minus 1 has to be 0. So, it means that this direction and this direction has to be orthogonal to each other. So, dot product has to be 0, and if you calculate the dot product we have this relation, that is z dash t naught equal to p naught x naught dash plus q naught y naught dash. Okay. So, for this reason we say that any set xt yt zt pt comma qt of 5 real functions satisfy the condition this, that is z dash t equal to pt x dash t plus qt y dash t, then it define a kind of strip. We say that it define the strip at the point x y z of the curve C. So, it means that if this thing, if p naught p1 satisfy this condition, then we say that the x naught, y naught, z naught, p naught, q naught as a function of t, this will define a strip, right. This is, so any function any phi function defined like this which satisfy this orthogonality condition, we call it a strip at p naught, right. Now, the set of function this 8 this which define a strip is also called an integral strip, provided they also satisfy the equation partial differential equation, that is f of x y z p q equal to 0. So, satisfy the partial differential equation means that the value of f evaluated at x t, y t, z t, p t and q t has to be equal to 0. So, using these ideas, now we want to find out the equation of the surface. So, for that let us say that at if at each point the curve touches a generator of the elementary cone, we call the corresponding strip a characteristic strip. So, it means that you take your curve, right, you have this curve. Now, if at each point if this strip you touches your Monge's cone, that is this thing, then we say that this strip is known as characteristic strip. Now what we try to do here, we try to generate this integral surface as totality of these characteristic strip. So we want to find out first of all what is characteristic equations, and then we look at the totality of characteristic equation, and then with the help of this we try to find out the integral surface. So for that we need certain results and results which we are going to prove it. So first of all we try to understand what is characteristic strip. A strip which touches the Monge's cone at each point of the curve is called your characteristic strip. So we first find out the equation of a characteristic strip. It means, or we can say that the equation of the Monge's cone, because your characteristic strip touches the Monge's cone at each of its point. So first let us find out the equation of Monge's cone, then generator of that. So the point x plus dx, y plus dy, z plus dz, which lies in the tangent plane of the elementary cone at P if it satisfies the following relation. So if this point lies in tangent plane, it must satisfy the following relation, that is dz equal to p dx plus q dy. So it is quite easy to find out, say dx dy dz dot p q minus 1, this has to be 0. So it means that here this point x plus dx, y plus dy, z plus dz lies in the tangent plane of to the elementary cone if the drs of the tangent line, that is dx dy dz, and normal vector to your elementary cone, and normal vector to elementary cone is p, q and minus 1, that must be orthogonal to each other, that is dz equal to p dx plus q dy. Now here p q minus 1 satisfy the equation 3, that is f of x y z p q equal to 0. So it means that on elementary cone, if you look at the normal vector, it satisfy the partial differential equation which we have started with. Now what we try to do here, we differentiate the equation number 11 with respect to p, and we have the following relation, that is dz with dp is simply 0. Now here we have p, so it is dx plus q is a function of p, that we have already noted down, that q is written as g of x y z p. So q is a function of p, so we differentiate with respect to p, we have dx plus dq by dp into dy. So here from this compatibility relation, that is dz equal to p dx plus q dy, we have the following relation, that is known as dx plus dq by dp dy equal to 0. But also we know that this p and q satisfy the partial differential equation f of x y z p q equal to 0. So differentiate this also with respect to p. So when you differentiate this with respect to p, then we have dever f by dever p plus dever f by dever q dq by dp and equal to 0. So using the equation number 13 and the previous equation, that is equation number 12, we can find out the relation between dx dy and dz, and that we can write it here. So here if you recall, the previous is what you can say dx plus dq by dp equal to, so here we have dx plus dq by dp dy equal to 0, and here we have this relation. So we can equate the value dq by dp from these two equations, and we can have the following relation, that is dx by fp equal to dy by fq, and you can get the ratio for dz, that is p dx plus q dy. So dx, so we can write here as relation between ratio between dz and this thing is p fp plus q fq. So it is a kind of a ratio, let us say k is a ratio constant. So we have the following relation for the ratios of dx dy dz, that is dx by fp plus dy equal to dy by fq equal to dz by pfp plus qfq, and when you solve this, that will gives you the equation of Monge's cone, that is equation of the elementary cone. And here you please recall that in case of Cauchy linear equation rather than nonlinear equation, in Cauchy linear equation your equation is pp plus qq equal to r, and if we denote this equation f of x y z pq equal to this, let us write it minus r in place of here let us say it is minus r. Then if you look at the value of Fp is your capital P and Fq is equal to capital Q, and Pfp plus Qfq is equal to what? Sorry, Pfp and Qfq is equal to r. So, this equation is now reduced to dx by P equal to dy by Q equal to dz by r, and that is how you find out how you solve your Cauchy linear problem, by solving these set of differential equation, and after solving this you can get the solution integral surface as a totality of integral curves. So, now here we are doing the same thing. Now, so that along a characteristic strip x dash t, y dash t, z dash t must be proportional to Fp, Fq and Pfp plus Qfq respectively. That is what this equation number 14 represent. Now, what we do, we can parameterize our curve as a, let us say, by taking this as dt here, then we can write down our equations, equation number 14 as the following thing: x dash t equal to Fp, that is here dx by dt equal to f of p, and dy by dt equal to f of q, dz by dt is Pfp plus Qfq. So, that is what I have written here in as equation number 15 and equation number 16. Now, along this curve which is parameterized in terms of t, your Pt and Qt is also a function of t, and we want to find out the P and T. Why? Because since in nonlinear problem corresponding to a given P, you may have more values of more than one values of Q. So, here you have to find out the equation for P and Q as well. So, we need to find out the relation for P dash T also. So, to find out the P dash T value here, to look at here, P dash T equal to del P by del x, x dash T plus del P by del y, y dash T. Here I am assuming that Pt is a function of x comma y, xt comma yt here. So, using this relation that P is a function of x and y are the functions of t. So, we can differentiate with respect to t, and we have this relation using chain rule: P dash t equal to del P by del x, x dash t plus del P by del y, P dash y dash t. Now, we already know the value of x dash t, that is f of p here. So, del P by del x Fp plus del P by del y, here y dash t is written as Fq, that we are writing here. Now, here we are using that del P by del y is what you, if you use this, this is what del P by del y is basically del by del y. Now, P is basically z of x, that is del by del y and del by del x z here, and you can write this as del 2z by del y del x. Now, if I assume that z is having second order continuous partial derivative, then this is equal to del 2z by del y del x del y, or you can say that here zxy is equal to z of yx. So, here I am assuming that your surface is smooth enough. So, assuming this, that zxy equal to zyx, we can write down py as q of x. So, replacing py by qx, we have p dash t equal to del P by del x, del f by del P plus del Q by del x, del f by del Q, and we have the relation by P dash t, using that P is a function of xy and xy is a function of t. But we also know that P satisfy the equation f of x y z p q. So, using this we can differentiate the f of x t, y t, z t, p t, q t equal to 0. If we differentiate this with respect to x, we have the following relation: del f by del x plus del f by z p plus del f by del p by del x plus del f by del q by del x equal to 0. So, right now I cannot use this because I really do not know whether this curve lies on the surface, or curve lies on this partial differential equation, or curve lies on the surface, we solve this. So, right now we simply use that f x y z p q is equal to 0. So, differentiate with respect to x, we have this relation. and here we can get this value which is written here P dash t is equal to this value. So, so here the characteristic on the characteristic strip your P dash t equal to minus of this value, that is minus of f of x plus p of f z. And similarly using the same thing, it means that using that q is a function of x and y, we can get this kind of relation for q also, and again we differentiate the equation f x y z p q with respect to y, and we can get this kind of relation, and using those two relation we can get the value for q dash t, and the expression for q dash t is equal to minus of f y plus q of f z. So, it means that if we collect all these equations, differential equation, then we have the 5 differential equation known as x dash t equal to f of p, y dash t equal to f of q, z dash t equal to p f p plus q f q, and p dash t equal to minus f x plus minus p f z, q dash t equal to minus f y plus q f z. And we say that after solving these 5 set of differential equation, we can get x t, y t, z t, p t and q t, and we try to say that these function 5 set function define a strip, and then we see that when this strip, basically these strips are basically characteristic strip, and then we say that totality of these strips will form a surface, and we want to show we want to find out the condition under what this conditions is an integral this characteristics define an integral surface, that we wanted to do. So, here for in this direction we have the following two result, that along every characteristic strip of the equation f of x y z p q equal to 0, then the value of f of x y z p q remains constant. So, to prove this, you simply differentiate with respect to t of f of x t, y t, z t, p t, q t, and when you differentiate you look at f of x, x dash plus f of y, y dash plus f of z, z dash plus f of p, p dash plus f of q, q dash. Now, here using the value of x dash, that is f of p, y dash, f of q, z dash, p f p plus q f p dash equal to this thing, and q dash is equal to this. When you simplify this, if you look at f of x and f of p, and this can be cancelled out by this term, f of y, f of q, this will be cancelled out here, f z p f p, that will be cancelled out here, and similarly this will be cancelled out here. So, we can say that d by dt of f of x t comma y t comma z t p t q t is equal to 0. So, it means that the value of f of x y z p q equal to k will remain the constant along the strip, right. So, this simply says that along a characteristic the value of f of x y z p q is equal to constant, but we really do not know whether it is 0 or not. To make it 0, we look at one more small result, that is that if a characteristic strip contains at least one integral element. What is what integral element? Integral element is the x y, the collection tuple x y z p q, such that the value of f of x y z p q equal to 0. So, if it contains one integral element, it means that if characteristic curves contains the value x y z p q such that f of x y z p q equal to 0, then of course the strip is an integral strip. It means the value of f of x y z p q equal to 0 along the characteristics for all values of t, right. What we have proven in this theorem 4, that along a characteristic your value of f of x y z p q has to be 0. Now, if it contains an one single element, it means that the value of f of x y z p q equal to 0 for one particular integral element, that is x y z p q, then the characteristic strip will be a integral strip, and once it is an integral strip, then we simply look at all the integral strips and look at the totality of these integral strips, and we say that this is the integral surface which we are looking for. So, that is the idea of this Cauchy method of characteristic. So, we try to find out the characteristic strip which contain an integral element, and this integral element is given in terms of initial data. So, let us look at here what is the strategy here. Now, suppose we wish to find the solution of PD2, which PD2 here is f of x y z p q equal to 0 and which passes through a curve C. Now, this is the initial data, means passes through means we want to find out a solution which contains this. It means that this curve is already on the surface which we are looking for. So, it means that this is your integral, this will define an integral element. So, let us define the this curve by a parameter say S. Now, S is lying in some interval, let us say it is closed interval a b, and C can be characterized by these parametric representation, that is x equal to f1s, y equal to f2s, z equal to f3s. So, here in a solution like this, x has x p naught, q naught, x naught, y naught, z naught, t naught and t. Of the characteristic equation, we can take x equal to f1s, y equal to f2s, z equal to f3s as initial values of x, y, z. So, it means that if these are the initial values, means at t equal to t naught, your initial value of your characteristic strips are basically x, f1s, f2s and f3s, then it will contain an integral element, and then the strips which we are looking for are integral strip, and in this way we can find out the integral surface. So, that is the idea of this. Now, we have only x, y, z. How to find out p and q? For that you can find out the initial value of p naught, q naught as follows, that is it satisfies this relation dz equal to p dx plus q dy. So, we can write this as dz equal to f3s. So, dz by ds you can write it, and this is ps and qs. So, initial curve is characterized by s. So, we can say along this initial curve your dz by ds is f3 dash s equal to p naught f1 dash s plus q naught f2 dash s. Also, along with this, because we want to find out p naught and q naught, we need two relation. So, one relation is obtained by this relation, that dr of tangent is perpendicular to normal vector, and another one is that these element will lie on the equation of the partial differential equation, that is f of x, y, z, p, q equal to 0. So, f of f1s, f2s, f3s, p naught, q naught is equal to 0. So, when we solve these two equations, we will get the initial value of x naught, y naught, z naught, p naught, q naught, and we have 5 differential equation, 5 ordinary differential equation along with these initial values, and if your fp, fq all these values like here which are coming here, that these fp, fq, these values are nice enough, then we can get a unique solution. So, here for this will have a nice value, because we have assumed that f has second order partial derivative in its argument. So, it means that fp, fq all these are continuous function, and we already know that in ordinary differential equation, if fxy is continuous, then also we have a solution, and if we are assuming more than that, that these functions satisfy the these functions are having one more partial derivatives. So, we simply say that this will have a unique solution along with initial condition that we have already obtained in terms of x naught, y naught, z naught, p naught and q naught. And after solving this, we have the following relation, that is x equal to x1 st, y equal to y1 st, z equal to z1 st. So, now we obtain the equation of the integral surface as two parameter family of integral family of surfaces. Now, if we want to find out the exact or surface, then you can remove your s and t from these three equation, and we can write down the equation of the surface in implicit form, like a psi of x, y, z equal to 0, and which is the integral surface of the equation 2 through the curve C here. So, that is the idea of this Cauchy method of characteristics. So, idea is what? So, that with the help of Cauchy method of characteristics, we first find out the characteristic strip. So, so it means that a strip which touches the Monge's cone at every point of its curve. So, at you look at the curve, and at every point if it touches the Monge's cone, then we call this that it will generate a strip which is known as strip, and now if it touches the Monge's cone, we call this strip as characteristic strip, and then we say that this characteristic strip is contain an integral element, then we call this as integral strips, and we look at the totality of these integral strips, then we say that we have a integral surface. That is the idea of this Cauchy method of characteristic. We will see some example to see that how this method work. So, that we are going to continue in next lecture, the example based on this method, and so thanks for listening, and we will continue in next lecture. Thank you.